Today we'll be learning the Bellman-Ford algorithm. So let us see what is meant by Bellman-Ford algorithm. Bellman-Ford algorithm. Okay, what is Bellman-Ford algorithm? This is to find the single source shortest path algorithm. Shortest path algorithm. So if you look at this sentence, you feel like you are familiar with this single source shortest path algorithm, which is this algorithm, which we already learned. Then why do we learn this Bellman-Ford algorithm again once we have one algorithm which is used to find this single source shortest path? The difference between this Bellman-Ford algorithm and this algorithm is Bellman-Ford algorithm allows the negative edges, whereas this algorithm doesn't allow the negative edges. There is a major difference between this Bellman-Ford and this algorithm. So let us see like how to find out the shortest path from a single source by taking an example. Suppose that we have one graph, directed graph 1 2 3, then 4 5, and we have 6 vertices, and we have one edge from 1 to 2 with a distance 2, and 1 to 4 we have 4, and 2 to 3 we have a negative edge minus 3, and 3 to 5 also negative edge, 3 to 4 also negative edge minus 4, and we have 2 to 4 1, and 2 to 5 5, and here 5 to 4 we have with the distance 4, and 4 to 6 we have 8, and also 5 to 6 we have one more edge with the distance 6. And let us consider this first as the first vertex as a source vertex. Let 1 is the source vertex. Okay, so now what we are going to do is we have to find the distance from 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6. What is the shortest distance from 1 to all other vertices in the graph? Okay, so for that let us list out all the vertices, and let us try to find out the distance between 1 to all the other vertices. Obviously from 1 to 1 it is 0. Okay, 1 to 2 it is, there is a direct edge from 1 to 2. So we are considering that with the 2 distance, and there is a direct edge from 1 to 3 which is whose distance is 4, and 1 to 4 this is like no, when there is no direct edge, what we are going to do is we are putting that as infinity, and 5 also there is no direct edge from 1 to 5, so this is also infinity. 1 to 6 also it is infinity in the first stage. After that if you see, so we can select the edge, no, we can select the vertex with the smallest distance from 1. So obviously the vertex 2 will be selected. Now what we are going to do is we are going to update these distances. How we are going to update these distances? 1 to 1 is obviously it is 0 only, and 1 to 2 it is 2 only. Now after considering this 1 to 2, so you are going to find out whether like this is 3 reachable via 2. There is a direct edge, that means 1 to 3 also we have, and also we can reach this 3 from 1 to 2 plus 2 to 3. So what is the cost of 1 to 3? It is 4, and 1 to 2 it is 2, and 2 to 3 it is minus 3. So which is minus 1. So this is the shortest distance. So we are going to consider this minus 1 here. And after considering this 2 as intermediate node, can we reach 4? Yes. So what is the difference? What is the distance from 1 to 4 via these 2? Because we have selected this 2. Okay, so that is nothing but 3. That is nothing but 3. Okay, then can we reach 5 via 2? Yes. Okay, from 1 to 2, 2 to 5. What is the distance here? This is 7. Can we reach 6 via 2? No. So there is no path from 1 to, I mean there is no direct edge from 2 to 6, that's why we are keeping that as infinity. Okay, then now among these we select, now we are going to, which is having a minimum value, that is 3. So now we are taking this 3. Okay, so now we are going to take this, consider this 3, and we are going to update all these distances. How 1 to 1 is 0 only, 1 to 2 is 2 only, and 1 to 3 is minimum is minus 1 only. Then now consider 1 to 4. Okay, so is it like we have, what is the distance earlier? It was 3. Okay, it was 3. That means from 1 to 2, 2 to 4. But after considering this 3, do we have the minimum distance? We had to check that. So how do we check that? So here the distance was 3. That is, earlier it was 3. And now after considering this, so that is 1 to 3 plus 3 to 4. 1 to 3 how much? Minus 1. And here this is minus 4. This is minus 5. So earlier it was 3 and now it is minus 5. So what we will be considering? The minimum distance. So minus 5 we will be considering. In the same way 5 also. 5, what was the distance earlier? That was 7. It was 7, and now if you are considering this 3 as an intermediate node, for 3 it is minus 1. So minus 1, and from 3 to 5 it is minus 2. So this is 7 and minus 3. So this is the smallest distance. So minimum distance. So we are going to consider minus 3. And what about 6? Because 2 and 3, only 1, 2, 3 are considered. So there is no direct edge from any one of these vertices. So this will remain infinity. Okay, next, if you see here, we have this fourth node as a, we can consider fourth node because it is carrying the minimum most distance. So now considering this fourth, we are going to update all the distances. So 1 to 0, 1 to 1 is 0 only, 1 to 2 is 2 only, 1 to 3 is minus 1 only. Next 1 to 4 is, we have already seen, this is minus 5, minus 5 only. Now 1 to 5 we have to consider. 1 to 5 we have seen that minus 3 was the minimum distance. Now after considering this fourth node, can we change this distance? So 1 to 4 was minus 5, and now if you are taking from 4 to 5, there is no edge, so there is no, we cannot reach that. So that's why what we are going to do is, we are not changing the distance, only minus 3 only we will be putting. And what about 6? So 1 to 4 it is minus 3, and 4 to minus 3, and 4 to 6 is 8. So minus 3 plus 8, it is equal to 5. So we are going to update this. No, sorry, this is minus 5. Fourth is minus 5. Minus 5 plus 8, this is 3 only. So this is 3. This is the distance. So this is the final distance which we are going to get. So what are the distances now we have? Because it's the smallest distance only, no, so we have obtained all the shortest distances already, so we have to stop the procedure here. So what are the distances? From 1 to 2, 1 to 3, 1 to 5, 1 to 5. So 1 to 2 is 2, 2 is 2, and 1 to 3 is minus 1, and 1 to 4 is minus 5, and 1 to 5 is minus 3, and 1 to 6 is 3. So these are the shortest paths, shortest distances from the single source. What is the single source here? 1 is the single source here. Okay, now let us see because no, only one thing we have seen, that is the formula. Which formula we had used here? Like already whatever the distance is there, and after introducing this particular node, what is there any change? Whichever is minimum, we are going to find out. So for that, how you are going to write the algorithm? So algorithm Bellman Ford, and we have V, that is the source vertex, and this is the cost. Okay, and this is the distance array, and n is the number of vertices. Okay, now now what we are going to do is, first we are going to take the distances. Okay, so for that we are using one for loop for I is equal to 1 to n do, and distance of I is equal to whatever is the cost, no, cost of V comma I. Okay, from that what like direct edges we are taking, like I is from 1 to n, like in the beginning we had seen, no, so this array we are initializing to distance of I. So distance of V is the vertex is 1, 1 to 1, 1 to 2, 1 to 3, 1 to 4, like that we are writing. So whatever the values we are writing here, those are assigned to distance in the beginning. Now because already we had chosen the first vertex as the source vertex, next start from the next vertex, that is k is equal to 2 to n minus 1 do. Okay, so here for each u such that u is not equal to v, and u has at least one incoming edge, at least one incoming edge do. Now what we are going to do is, for each edge, so in this, under this, for each I comma u in the graph, I'll explain this. In the graph do, if distance of u is greater than distance of I plus distance cost of I comma u, then so distance of u is equal to distance of I plus cost of I comma u. Okay, so that's all. This is the algorithm, I comma u. This is the algorithm. So what do you mean by that? So for each u such that u is not equal to v, right? So that is not the same vertex. Okay, so u has at least one incoming edge. So if you consider this, suppose fourth if you are considering, so here this is we are considering this 2. So 2 to 3, do we have any edge from 2 to 4 we are taking, no? From 2 to 4, is there any incoming edge from 2 to 4? Yes. In that case, you are going to update for each I comma u in the graph, distance of 4, u is 4 now, 4, distance of 4 is greater than distance of I. So what is I here? I is 2, because we are considering this I and this is u. So what is the distance of I is, distance of I is equal to 2. Okay, distance of this one, and also 2, distance of I is equal to 2, because here this one. Okay, and plus cost of IU, that means what is the cost of 2 to 4? That is 1. So what is that? 3. So earlier what was the distance? Infinity. So if that infinity is greater than 2 plus 1, that is 3, yes, then you are going to update the cost of u, that is cost of 4 is equal to distance of that I plus cost of IU. That means distance of 4 is nothing but so this distance plus this cost of this one. What is the distance of 2? That is 2 plus cost of this 2 to 4, that is 1. So that is equal to 3. We are going to update that. In the same way, all the other remaining vertices also we will be updating all the edges here, all the values here. Okay, so this is about the Bellman Ford algorithm, and I hope you understood this.